Hello, Math 300, and this is Mr. Gonzalez. And I'd like to, well, first of all, hope everybody is healthy out there. But I'd like to take some time to go over the problems in 10.5 and kind of just touch base on that. This first one, let's take a look at it. And it says, if you toss 5 fair coins, in how many ways can you obtain at least one head? Now, the way the book is looking at this is that you're going to use the fundamental counting principle, which says that there are two ways to flip a coin, two outcomes, right? Head, tails. And then you're going to do it again, and there's two of those, and then there's two more ways. And then when you flip the coin the fourth time, there's two ways, heads or tails. And then the fifth time, there's two ways, heads or tails. And when you multiply that up, you got 2 times 2 times 2 times 2 times 2, which is 32. And then when you're looking at how many ways can you obtain at least one head, well, there's a lot of those, right? When you're flipping the coins, when you're flipping them tossing 5 fair coins, when you're counting different, out of the 32 possible outcomes, the only one that doesn't have at least one head is just the one possibility that is would be no heads or all tails, right? So that's kind of how they're looking at it. They're looking at it like looking at the complement of no heads. So they're saying, well, there's 32 total possibilities when you're flipping 5 fair coins, and there is one way. Now we're looking for how many ways have at least one head, but if we look at, well, there's one way to have no heads. So if we look at its complement, right, 32 minus that's going to give us how many ways that we're going to have at least one head. So that's going to be 31. So the answer is 31. I think that's not always super intuitive. So what I did was I took some time, and you kind of want to get this idea of a complement down, because when the numbers get really big, it's really hard to visualize. This is sort of, in my opinion, on the edge of visualizing it. So what I'm going to do is go down to this tree diagram I made of this, and it was kind of a pain. You can see that tree diagrams are great, but can be limited because of how much time and space it can take to do that. But what this shows us is let me go back to pencil. It shows that I've got I flipped the coin the first time. So here's the first time, right? And what are my outcomes when I flip the coin? What could be a heads or it could be a tail, right? So that would be a 2. And then I flip the coin the second time. And when I flip the coin the second time, it could be a head or tail. And I flip the coin the third time, it could be a head or a tail. And I flip the coin the fourth time, and it could be a head or a tail. And I flip the coin the fifth time, it could be a head or tail. And you can see this multiplication thing happening. When I'm flipping, let's say the second time, well, you've got 2 times and then 2 more possibilities, right? So 2 times 2, now we have 4. 1, 2, 3, 4. 4 times 2 is 8. Well, there's 1, 2, 3, 4, 5, 6, 7, 8. So you kind of see how this fundamental counting principle is working by using multiplication. And so, in fact, if we were to, this is still problem number 1, by the way, but if we were to count out all these possibilities, there would be 2 to the 5th power, which is 32. And you could literally count these out, right? So they said, in how many ways can you obtain at least one head? Well, when you're visually seeing this, you can say, well, this is a H, 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 H. So those are all heads in a row. So anything that branches off of this is going to be heads, right? Because it at least has one head. And you go down here, well, this is a tail, but then that is a head. So all those possibilities have at least one head. And you keep on going down. Well, I've got a tail, and then if we branch this way, well, that's a head. So the only way, right, the only one that doesn't have at least one head is this last possibility of tail, 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 tail. So instead of counting 1, 2, 3, 4, 5, 6, and getting up to 31, the idea is that you take the total 32 and subtract out, instead of getting, so we're looking for at least one head, well, you look at its complement, which means no head, and there's only one way to do that. And so you say 32 minus its complement is actually going to give us the answer of how many ways can we obtain at least one head, so that's 31. So I hopefully that was worth something. I tried to give you a visual on what was going on with that. And some of the stuff is a little bit hard to imagine or think about, but I think the visual definitely helps. You can follow along. I try to use color here, showing you that the green H's, right, that, all of these possibilities have at least one head involved when we're counting 5 tosses. The only one that does not have a head is going to be tail, 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 and tail. And so that's where we are able to look at that, take its complement, which gives us 31, which is at least one head. Okay, this idea actually is really useful. Let me sort of flip this around so we can have a better writing surface. This idea becomes really useful. And some of our later problems, like number 10, I think, and 11, those ones where you want to use the complement because it's just, it's just too many possibilities out there. Okay, well, let's go ahead and move on and get back to our problem here. Okay, so here we are. It says, if you roll 2 fair dice, one black and one white, in how many ways can you obtain the sum of at most 11? Okay, the sum of at most 11. Well, I've included this chart, this dice chart. Let's see, here it is. The dice chart in Canvas that you can download if you like. And so what does at most 11 mean? Let's think about it. Is 6 at most 11? Yeah, 6 is in that category of at most 11. 8 is in at most 11. 9 at most 11. Is 10 at most 11? Is 11? 11 is at most 11. Is 12? No, 12 is not at most 11. So the values that we're looking at, right, are all of these. And I really don't want to circle all of them. All right. Anyhow, you got the idea. Now that I start, I feel like I have to circle all of them. Go, go, go. And so all of these circled, all these circled values would be at most 11. So if we counted all those up, that would be what, 35. All right, let's go back. Oh no, now I've got to erase all this stuff. Let's see. So that it would be 35. So the answer for number 2 is 35. Let's go back up there. Number 2, answer is 35. All right. Let's take a look at the next one. Let's see. Okay, there we go. Number 3. If you roll 2 fair dice, one black and one white, in how many ways can you obtain 1 on at least 1 die? 1 on at least 1 die. Okay, well, let's take a look at that. Go to the dice. So you could think of this as this maybe being die number 1. Oops, number 1. And this one is like die number 2. And remember, we're rolling these 2 dice. So to get this 2, you had to roll a 1 and a 1. So that's at least 1 on one of the die. To get the 3, you had to roll a 1 and a 2. So all of these sums in this row must have been the sum of a number like this one, 6 plus 1. So these all have at least 1 die in them, or a die of 1. What's the verbiage? In how many ways can you obtain a 1 on at least 1 die? Okay, so that takes care of that. Well, then we've got this die. So we first looked at this one, but now we've got this die to look at. We don't want to double count this because to get a 2, you get a 1 and a 1, right? So that's at least 1 die. That's just counting as one count that does that. A 1 and a 3 is at least 1 die. A 1 and a 2, which makes a 3. A 1 and a 3, which makes a 4. and so on. So these are all the outcomes that will obtain a 1 on at least one die. And how many would that be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the answer is 11. All right, let's go back. And there we go. Okay. 11. Number 4. It says, if a single card is drawn from a deck, a standard 52 card deck, in how many ways can a card other than a heart be obtained? Okay, in how many ways can a card other than a heart be obtained? Okay, well, other than a heart, well, let's take a look. And you could download this also, right there. How many ways can a card other than a heart be obtained? Okay, so no hearts. So get rid of the hearts. Other than a heart, well, how many would that be? Well, there's 13 in each suit, right? So there's 13 clubs, there's 13 diamonds, and there's 13 spades. And when we take 13 times 3, we get 39. Okay. So on number 4, in how many ways can a card other than a heart be obtained? You've got 39 ways, or 39 possibilities there. Number 5, Gina's collection of 7 albums include 1 rock album. Gina will choose 3 of her albums to play on a road trip. Okay. Assume, this is kind of nice, it tells assume that order is not important. Okay, let's do A over here. Assume that order is not important. Letter A. How many different sets of 3 albums could she choose? Order is not important, so we're going to use a combination. How many different sets of 3? So we're choosing 3. How many different sets of 3 albums could she choose? Well, how many albums does she have? Gina has a collection of 7 albums. Okay, there we go. So it's 7, choose 3, and this is a combination. So we just use the formula for combination, which is 7 factorial over 3 factorial times, remember that, 7 minus 3 factorial. And I showed you on the last one how to simplify that. Let me go ahead and do it on this one, and then I think we'll just kind of cut to the chase. We write this as 7 times 6 times 5 times 4 factorial. And 7 times 3 is 4 factorial. And so that will nicely and neatly reduce common factors. And don't forget, because this is a combination, we still have 3 factorial. So we got 3 times 2 times 1. And we also know that 3 times 2 is 6, which is going to reduce with 6, which leaves us with, what is that, 7 times 5, which is 35. So part A is 35 different combinations for 7 albums, choose 3 at a time. Okay, let's take a look at B. Okay, B says, how many of these sets would not include the rock album? Okay, well, there's only 1 rock album, so if it's not going to include the rock album, there must only be 6 of them that are not rock albums. So we have 6 possibilities, choose 3. And this is going to be 6 factorial over 3 factorial. And then, of course, it's 6 minus 3 factorial. And when you simplify that out, we get 20. And letter C. How many ways, how many of them would include the rock album? So, you got a couple different ways to go about this, but probably the best way to do this is to realize that if we have the total, for some reason my sleeve is causing this thing to jump around. You have the total, if we have total sets of 3. So we have total sets of 3 and we subtract out the sets of 3 that do not include rock. Did not include rock, or the rock album. That is going to be the sets of 3 that would include the rock album. So the nice thing about this is we already have some of this information. How many total sets of 3 are there? Well, that's part A. That was what, 35? Use another color for that. That'd be 35. And then, because remember what we're looking for. How many of them would include the rock album? Well, we got 35 total. And then we have how many sets do not include the rock album? Well, that was part B. There are 20 sets that do not include the rock album, so that's going to be part B. And that would give us the sets that would include the rock album. Okay, so that gives us 15. And that'd be the easiest way to do that. Okay, let's take a look at the next problem. Number 6, a system of identifying call letters uses call letters that begin with either a Y or an F. Some have a total of 2 letters, and others have a total of 3 letters. How many different call letter combinations are possible? Count possibilities even though practically some may be inappropriate. Okay, do not apply combinations. So they're giving us some hints there. So on number 6 here, I'm going to use the counting. Oh, what is that? Jeez. Okay, we're going to use the fundamental counting principle. So let's look at this first. I think I'm going to use some colors here. Some have a total. Let's do this. For some reason that's not working. There it goes. Some have a total of 2 letters. Now we know they said that they're starting off, the first letter has to be a Y or T. So I'm going to just do this. Y or T. Y or T. So that's only 2 possibilities for that. And then the second can be any letter, right? So that's going to be, there's 26 in the alphabet. So fundamental counting principle, when you say 2 times 26, you get 52. Okay, then we can take a look at, and others have 3 letters. The same thing applied, that they said, well, the first letter could be a Y or a T, so that would be 2 possibilities. And then we've got 26 letters in the alphabet, so 26 possibilities. And they said do not apply combination because they're allowing for repeating. So then there's still another 26 because you can repeat possibilities on the third letter. They told us 2 letters on the first one, it had to be a Y or T, and then 26 possibilities on the second letter, and then repeats are okay, 26 still. When you multiply 2 times 26 times 26, you get 1,352. And when you take a 1,352 and then you add that to 52, right, you're going to get a grand total of 1,404. 1,404. And remember, something that's a little different than combinations and things like that in the past, combinations, permutations. This one is repeats are okay. Repeats are okay. All right. All right, let's take a look at the next problem, which is number 7. If a single card is drawn from a deck of 52 cards, or deck of 52 card deck, in how many ways could it be either a diamond or a face card? Okay, so now this gets into the additive principle of counting. or addition principle of counting. And this actually is something we looked at prior, way back at the very beginning of the semester when we were doing set theory, I believe it was. Yeah, that was what we did at the beginning. And so let me kind of review that and show how that ties together in what we're doing right now in number 7. So back then, I gave an example like this. Let's see, let me make sure I have space for the next problem. I gave an example like this. I said, okay, if we had set A and we had set B, you guys remember this one? And I had 1, 2, 3, 4. So set A is 1, 2, 3, 4, and set B is 2, 4, 6, 8. And remember the symbol for cardinality. It said, so remember cardinality. Which is basically just counting the number of elements in a set. So that's kind of what we're doing with our counting, combinatorics or counting of these systems, right? We're looking at cardinality in a way, right? So back then in our first test number 1, we would have said something like, okay, well, if you want to count how many, now when you're looking at this, I'm giving you a simple example just so you can see everything. And then as the number, as you know, our examples have much bigger numbers, you want to have this principle down so you don't have, because a lot of times you just can't visualize it because, you know, there's too many things. But here's the main idea. You can see, if I said how many elements are out here, you would just said there's 1, 2, 3, 4, 5, 6, right? Because you can just see it. But if these sets were so big you just couldn't see it, what the cardinality rule is talking about, it says, so what is the number when you have set A, remember that, union B? Well, we said it was going to be, find the cardinality of set A plus the cardinality of set B. But remember what happened, and you can see it happening here. What's going on here is that we're accidentally double counting A intersect B. So that has to be subtracted out. Oops, I'm out of space, aren't I? I think I could fit it in. A intersect B must be subtracted out. And so you can see how that works. Okay, now fast forward to counting or combinatorics. This same thing can be used, and we just call it the additive principle. Additive principle of counting. Okay, and it looks the same. It looks the same, right? We could just say, okay, the number, if we want to know the number of set A, now I'm going to use the word or, because or is the same thing, but that's what you're going to see with the problems in chapter 10. So I want to know how many elements, or what's the number of elements that are in set A or set B. And it's going to be the same formula. It's going to be the number that's in set A plus the number that's in set B. And then, of course, subtract out, as long as there's overlap, right? Then you have to subtract out the number that's in set A. And then we use the word and, because and is the same as intersection, and or is the same as union, okay? So when we actually go through this problem, we would say, all right, well, how many elements are in set A? Well, there's 1, 2, 3, 4, so there's 4. And how many elements are in set B? Oh, there's 2, 4, 6, 8, so there's 4. We know that we accidentally double counted the intersection, or and. How many elements are in set A and set B? Well, that's this intersection, or the and case, so we have to subtract that out because there are 2 of them in there, 2 and 4. And so this is the additive principle of counting. that you want to apply, especially when the sets get, super large. When we add all this up, we have 8 minus 2, so we get a total of 6, just like we saw from the very beginning. Of course, you wouldn't do all this with such a simple problem. But once again, you want to have this additive principle of counting in your head so you can apply it to when problems get tougher. So let's see what that looks like down here. Number 7, and we're going to apply it here now. So on number 7, it says a single, I think I already read it. In how many ways could it be either a diamond, or, man, that's really what you want to focus in on, that or face card. Okay, so we want to know, and do I want to use color on this? I don't know. So, yeah, I do, I think. So let me go use some color. So we basically want to know, what is the number of diamonds? And then using this new rule that we remember from the past, we have to add the number of diamonds plus the number of, what was the other thing? Face cards. And then if there is any overlap or intersection, you got to take that out. So are there any? So what are the number of diamonds and face cards? Those would be the ones we accidentally double counted. So let's go down and see if we can make sense of this. Remember I told you that download that I set for you guys right here can be really useful. Let's go ahead and erase some of that stuff. So we got a clean slate to work on. This is a high-tech slate called an iPad. But anyhow, this is, what number are we on? So we're looking at the number of diamonds. Okay, oops, I still need to erase that. There we go. So the number of diamonds, well, isn't that going to be this stuff? Those are all diamonds, aren't they? Well, that would be 13. Okay, let me write that down. Maybe that's not a good idea going back and forth, but that would be 13. Okay, now we need to see what are the number of face cards. Well, face cards are all these cards with faces on them, I think, right? Not a big poker player, but I think I can figure that out. It's going to be all these things right here. And there's going to be, what, 3 times 4, 12 face cards. So let's go back here and put 12. Number of face cards, 12. So that'd be great unless there are some of these cards that we double counted. And the double counted cards are going to be the overlapping cards. Basically, the cards that are green or are green and, would be the right language, and red. Let's see, what is green and red? Green and red, that's going to be these 3 cards right here that are diamonds and face cards. So we have to subtract out those 3 because we double counted those. We double counted. So minus 3. This gives us a total of 22. All right. If a single card is drawn from a standard 52 card deck, in how many ways could it be either an ace? Okay, here we go again with some color. An ace, or should I go with a different color? So yeah, maybe it shows up better. Or a club. And of course, really, really important to see the or. So now we know what to do. We know that we just use our rule for counting. It's the additive principle of counting. Okay, so we take the number of aces, and then we want to add that to the number of clubs. And then, of course, subtract out if there's any overlap or intersection. So we've got to subtract out if there are any of them that happen to be an ace and a club. All right, let's go to our deck of cards. And you're gonna have to clean up here a little bit and see if I can get this thing to, okay. I don't know why it's too, there we go. All right, so my colors, I believe, were green and blue. So the first question was, how many are aces, the number of aces? So let's show that right here. So there are my aces. So that would be 4. Number of clubs. Number of clubs. Now clubs, kind of a weird name for this clovery thing, huh? I think there's a whole history on that, but let's not get into that. So that is a club. Those are all the clubs. You could already see, right? There's our overlap that we have to subtract out because we're double counting that. Anyhow, there are 13 clubs. So that would be 13. And since I already pointed out, I'm not going to go back. I add 4 plus 13, and there is one card that happens to be an ace and a club. So that must be subtracted out because I double counted that. This gives us a total of 16. And that is the answer. Next. So this idea works on quite a few problems. Anytime you see an or an addition, you have to watch out if you're accidentally double counting. Let's see what this says. The table at the right, now this is a two-way table, which is notorious for this kind of problem that has an intersection that you got to watch out on double counting. Excuse me. The table to the right categorizes 25 senators as to political party and gender. One member is chosen at random. In how many ways can the chosen person be a woman? Oh, there's our language. So let's make sure we got that. There's be a woman or Republican. And what's really important is that you see the word or. Because once you see that word or, you know we're adding and then subtracting out anything we double counted as an overlap. Okay. So let's start off with woman. So, oh, I got the wrong one. Come on, there we go. So, how many women are there? Well, they give us everybody in this, right? There's 2 Democratic women and 5 Republican women, so there's a total of 17. And then what about the number of Republicans? Well, Republicans, there's 2 men and, so let's go like this. 17 Republicans total. And we just have to make sure, did we accidentally double count? And you can see it right there. Did we double count? Yes, there are 15 women that are Republicans, which means we accidentally double counted that. So this is going to give us 17 plus 17 minus 15, which is a total of 19. 19, a person who's a woman or Republican, that would be 19. And, you know, if you went through this and added 2 plus 15 plus 2 plus, let's see, wait a minute. Yeah, if you said 2 plus 15 plus 2, right, then you wouldn't have double counted it. But when you're trying to count all women and then trying to count all Republican, that's when we accidentally double count, and that's when we have to subtract out. All right, so there's that idea. That's an important idea to get, and once you have that framework and kind of gives you a plan to deal with these problems when you see that language of or. Next is this problem, and this problem brings us back to problem number 1, where using its complement is going to be much easier to work with. Remember when I took all that time to make that tree diagram at problem number 1? and counting all those possibilities, it was easier actually just to say total minus its complement. But that's kind of comes up again here. So what's going on here? It says among the 2,598,960 possible 5-card poker hands. Oof, where'd they get that from? Well, they got that from, now remember, poker hands, or when you're dealt cards, the order does not matter, because if you have a king and then you get an ace, it didn't matter if you had an ace and then a king. The order doesn't change your hand. Okay, so it's definitely a combination. Let's do this down here just as a note, just so I can show where that number came from. They just gave it to us. They just gave that number to us, which is fine. But 2 million something, right? Where did that come from? Well, that just came from if you're trying to find the number of combinations of a per poker hand, it's going to be, you have 52 cards, and of course there's no repeats, because once you get a card, you can't get it again. If someone deals you an ace of spade, you're not going to get another ace of spade. Okay, so it's going to be a combination of 52. Choose 5. Whoa, that just got bigger all of a sudden. See if I can go back. Come on. Okay, it's acting weird. Anyhow, of course this is just going to be 52 factorial over 5 factorial times 52, minus 5 factorial. And I'm going to spare you the details, but if you simplify that or put it on the calculator, you will get to 2,598,960. So that's where that came from. And they just, so that was just done for you. And so let's get into the actual problem here. Problem number 10. Possible 5-card poker hands from standard 52 card deck. How many contain at least one black card? There's that at least one black card, and they know that this is a hard concept. So they're telling you, they're giving us a big old clue that at least one black card, it's going to be the complement of all red cards, right? So at least one black card is the same thing as the complement of all red cards. So let's find out all red. How do we find all red cards? Well, all red cards are going to be a combination. Now remember, we're choosing 5. How many red cards do we have? Let's see. 26 red cards. So we go back up here, and that would be, so 26 red cards, and we want to put them in groups of 5. So 26, choose 5. Of course, that is going to be, well, let's go ahead and just, I've done a lot of those, so I'm going to let you go ahead and do that. And when you figure that out, we get 65,780. So these are the ones that are all red. So let's get a game plan here. We want to take the total, and then we want to subtract out the groups of 5, right? The poker hands that are all red. And when we do that, that's going to leave us with the hands that are at least one black card. So there's that complement idea that's really powerful. So we already know that the total possible 5-card poker hands, well, that was given to us as 2,598,960 minus the all red poker hands, which was 65,780, and that gives us the result of 2,533,180 poker hands that have at least one black card. All right, let's do it again. Number 11. So same setup among the 2 million blah 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 possible poker hands. How many contain, and let's use color again. How many contain at least one spade? So, they're giving us the clue, the answer. So to get at least one spade is going to be the same thing as getting the complement of no spades. So that's our clue. We should be trying to figure out no spades. Let's do no spades in green here. So we want to figure out no spades. I don't know. I have no space for no spades. Let me see if I can do this. No spades. Okay, well, it's going to be combination, groups of 5. So no spades. Let's see what that means. Let's go to our deck of cards. And no spades. Well, these are the spades right here, right? So if someone says no spades, well, then you could have hearts, you could have diamonds, you could have clubs. Well, that's 3 times 13. And we already know 13 times 3 gives us 39. So we've got 39 cards to choose from, making groups of 5. And when you figure out 39, choose 5 as a combination, you will get 575,757. Okay, so using the plan that we had before, which says if I take the total ways of building 5-card poker hands and I subtract out, and this is where they give us the clue to do that. They subtract out the no spades. So when you take the total minus no spades, that gives us the complement of spades, which is exactly equal to at least one spade. So total minus no spades is going to give us at least one spade. All right, let's do it. Total once again, 2,598,960 minus no spade, which we calculated in green, so we'll stick with that. That was 575,757, and we get a grand total of 2,023,203 hands that have at least one spade. And finally, the last one in a 5-card poker, a royal flush is an ace, a king, a queen, a jack, and a 10, all of the same suit. How many ways are there to get a royal flush? Well, they have to be the same suit, right? So there's not that many ways. When you look at this, you can get a royal flush. Let's make a pink one. What would the royal flush be? I believe it was, what was it again? It was an ace. It has to be the same suit though. Ace, king. Why can't I see there it is. King, queen, jack, and a 10. There's your royal flush. And of course, so there's one way of getting royal flush, and then you could do that in diamonds, and you can see where this is going. You can do that with hearts. You're seeing where this is going. So we've got 1 hand, 2 hand, 3 hand, and we've got one more way to make a royal flush. That would be with spades. So how many ways can you make a royal flush? 4 ways. And that is it. So I hope that helped out. That is going over all the problems in 10.5, and hopefully that helps out. You can use this to complete those problems in the homework, and it's also a good study guide when you're practicing with the review and doing the test. Okay, take care. I hope everybody is sick-free or ill or free of any kind of sickness, viruses, such. And I hope you have a great day. I'm signing off, and take care.